Welcome to today's Explainer. We're diving straight into a curious mathematical wonderland today, a place where the everyday words we just casually toss around aren't exactly what they seem. We're going to explore this fascinating intersection of math and language, looking specifically at how math borrows our everyday vocabulary but then applies an incredibly strict set of rules to it. Our main focus? Untangling the often confused concepts of permutation and combination. Because by the end of this explainer, you're going to look at some incredibly ordinary objects and the actual words you use to describe them in a completely different light. Okay, let's dive right into this. Consider this incredibly familiar everyday item. We have all used them, right? On our lockers, at school, at the gym, on our luggage. And without even a second thought, we all confidently call this piece of hardware a combination lock. It's totally ingrained in our language. You spin the dial, you enter the combination, and the lock clicks open. Simple enough, right? Well, here is where we introduce our rabbit hole for the day. I want to shatter the illusion we've all been living under and ask a fundamental mathematical question. Is this everyday name actually accurate? Like, does calling it a combination lock make any actual mathematical sense? Because as we're about to see, the world of mathematics absolutely demands precision. And this little lock, it's hiding a major secret about how it operates. To solve this mystery, let's actually test the lock's logic. Let's say the secret code to open your lock is 372. Now, what happens if you spin that dial and enter 273 instead? You're using the exact same numbers. The ingredients are literally identical, but as we all know, if you enter them backwards or jumbled up, no way that lock stubbornly refuses to open. And this highlights our guiding mathematical question for today. Does the order matter? Clearly, for our lock, just having the right numbers isn't enough. They have to be in the exact right sequence. Which brings us to the first undeniable ground rule of our mathematical wonderland. We need to define a word that perfectly captures what that lock is actually doing. And that word is permutation. A permutation is an ordered arrangement where position is absolutely critical. In permutation thinking, the specific seat that a number or an object occupies totally changes the identity of the entire group. It pays very, very strict attention to position. And this is brilliantly illustrated using just a few simple letters. If we take the letters A, B, and C and arrange them as A, B, C, that is one specific permutation. If we simply swap the first and last letters to make C, B, A, mathematically speaking, we've created an entirely different arrangement. Even though we're looking at the exact same three letters, the order has changed. Because order matters here, A, B, C, and C, B, A are just not equal. Let's look at the math behind how we actually count these arrangements. If you want to arrange those three letters, A, B, and C, how many ways can you realistically do it? Well, for the very first spot, you have three choices. Once you pick a letter, you only have two choices left for the second spot. And for the final spot, you just have one choice remaining. Multiply those choices together, 3 times 2 times 1, and you get 6 unique permutations. In mathematics, we actually have an elegant shorthand for this countdown. We write it as 3 factorial, which is denoted by a 3 with an exclamation point. All right, it's time for the grand reveal, the conclusion to our first mystery. Because the exact order of the numbers strictly matters to get that lock to pop open, it is living a lie. It's not a combination lock at all. Based on the strict rules of mathematical language, it should properly be called a permutation lock. The everyday name has been completely misleading us about the underlying math this whole time. So that realization naturally pushes us to the other side of the dichotomy, doesn't it? If our trusty lock isn't actually a combination, then what is? What does a true combination actually look like in the real world when we apply strict mathematical literacy to the term? Let's define it right back to back with our earlier rule to see the contrast. A combination is a selection where order simply does not matter. In this part of the math world, we only care about which items are selected to be part of the group, not the sequence in which they arrived. It's a completely unordered selection. To really ground this math in reality, let's think about making fruit juice. Say you want to blend a delicious smoothie, and you choose an apple, a banana, and a mango. If you toss the apple into the blender first, then the banana, then the mango, you get your juice. Now, what if you tossed the mango in first, then the apple, then the banana? The blended juice tastes exactly the same. The end product is identical regardless of which fruit went into the blender first. Because the order doesn't change the outcome whatsoever, this is a true mathematical combination. And this difference completely changes how we calculate them. When we counted permutations of 3 things earlier, remember, we got 6 different arrangements. But with combinations, like our 3 fruits, those 6 different orders, apple, banana, mango, mango, apple, banana, all of those, they all just make one unique glass of juice. So to calculate combinations, we first find the total permutations, and then we have to shrink that number down. We divide our total by the number of ways those specific items can be duplicated or rearranged, leaving us with only the true unordered combinations. Now, what's really interesting about this slide is how asking one simple question acts as a universal compass. Does order matter? For a lock code, yes, it absolutely does. It's a permutation. For the results of a 100-meter dash where you hand out gold, silver, and bronze medals, yes, order matters immensely, permutation. But choosing fruits for a juice? No, it's a combination. Selecting 3 students just to be on a team together? No, order doesn't matter there either. It's a combination. That one single question instantly categorizes our everyday situations. This whole lock versus juice dilemma actually transitions us to a much broader lesson about math literacy. The truth is, mathematics often borrows our everyday words, but then it gives them highly precise, strictly enforced, and honestly, sometimes completely different meanings. Everyday words basically wear strange disguises in the math world, which is exactly why that combination lock confused us in the first place. Let's juxtapose another really common word to see this in action. Take the word group. In an ordinary, everyday classroom setting, a group means students collaborating, right? The focus is entirely on working together. But in advanced mathematics, a group is an incredibly specific algebraic concept. It's a set of elements paired with an operation that satisfies very strict structural rules. Same exact word, but 2 entirely different worlds of meaning. And you can see how this builds across a whole Wonderland dictionary of terms. Think about the word ring. Ordinarily, you'd think of jewelry. But in math, it's a specific algebraic structure. Field goes from a place where you grow crops to a complex number system. The word normal shifts from meaning ordinary or average to meaning perpendicular in geometry. This brilliantly illustrates that part of becoming math literate is developing the reflex to ask, okay, what does this word actually mean in this specific mathematical context? Let's put this curiosity to the test with a few everyday scenarios. Arranging books on a shelf. Does order matter? Well, yes, if you care which book is first and which is last. So that's a permutation. Choosing 3 pizza toppings. Well, whether you say pepperoni then mushroom or mushroom then pepperoni, it's the exact same pizza. Order doesn't matter. Combination. Creating a 4-digit passcode for your phone? Just like our lock, order absolutely matters. Permutation. So, the crucial point is summarized perfectly by this idea. Mathematics is not only about calculating, it is also about reading words carefully. True math literacy requires looking beyond just the numbers and the formulas to really understand the precise language being used to describe the structures around us. I want to leave you with a final, lingering cognitive trigger. The next time you walk up to a locker, the next time you blend a smoothie, or even the next time you encounter a totally familiar word in a math text, just pause for a second. Ask yourself the most important question of this explainer. Does order matter? Because as we've seen today, the answer to that question changes absolutely everything. Thanks for exploring this mathematical wonderland with me today.